assistant less than, end underscore header underscore id, greater than. Causal discovery tasks in observational settings face significant challenges due to unobservable links and identification problems. Traditional regression approaches often rely on assumptions that may not hold in complex systems, leading to inaccurate results. Recent breakthroughs have introduced new methods for investigating causal relationships, allowing for the explicit formulation of underlying mechanisms and the estimation of causal effects. One major challenge in causal discovery is the presence of confounding variables, which can lead to biased estimates of causal effects. To address this, researchers have developed methods that can identify and account for these variables, such as instrumental variable analysis and causal graphical models. These approaches can provide more accurate estimates of causal effects and help to establish causality in complex systems. Another key aspect of causal discovery is the evaluation of causal models. This involves assessing the validity of the model and its ability to capture the underlying mechanisms of the system. Researchers use various metrics, such as goodness, fit, and predictive accuracy, to evaluate the performance of causal models. Additionally, techniques like cross-validation and sensitivity analysis can help to identify potential biases and limitations of the model. Recent studies have also highlighted the importance of considering multiple causal relationships and interactions between variables. This can be achieved through the use of Bayesian networks and structural equation modeling, which can capture complex relationships between variables and provide a more comprehensive understanding of the system. Despite these advances, causal discovery remains a challenging task, particularly in the presence of complex systems and limited data. Future research should focus on developing more robust and efficient methods for causal discovery, as well as improving the evaluation and validation of causal models. The authors of the original paper compared the performance of different causal discovery methods and found that some approaches outperformed others in certain scenarios. They also highlighted the importance of considering the underlying mechanisms of the system and the need for more robust evaluation metrics. Overall, the paper provides a comprehensive overview of the challenges and opportunities in causal discovery, highlighting the need for continued research and development in this area. By improving our ability to discover and evaluate causal relationships, we can gain a deeper understanding of complex systems and make more informed decisions in a variety of fields. The paper presents the linear latent variable structural equation model with measurement error, LVSEMME, a statistical model used to analyze relationships between variables in a system. It aims to provide a formal description of the model and explore the problem of recovering the model from observational data. The model consists of two sets of variables, v and x. Variables in V can be arranged in a causal order, with each variable generated as a linear combination of its direct parents and an exogenous noise term. The variables in V are further partitioned into three sets. Y, Z, and H variables in Y are observed without error, while variables in Z are measured with error, and variables in H are neither observed nor measured with error. The authors define a measured leaf variable, M-leaf variable, as a measured variable in Z that has no other children besides its noisy measurement. They also define a cogent variable as a variable in Z union Y that is not an M-leaf. The paper adds two restrictions on the model for the sake of model identifiability based on observational data. Firstly, for any M-leaf variable Z, the exogenous noise term NZI is not distinguishable from its measurement error NXI. Secondly, the authors assume that the model satisfies the faithfulness assumption, which means that the conditional independence relationships in the data are due to the underlying causal structure of the model. The paper focuses on identification analysis, where the authors demonstrate the extent of identifiability under their two versions of faithfulness assumption. They provide such results first in two submodels where they need to deal with only unobserved common causes or only measurement error, and then they consider the case that these two challenges coexist. The authors also present their recovery algorithms for the LVSEMME in Section 4 and conclude in Section 5. Identifying linear latent variable models with measurement errors is contingent upon specific assumptions and restrictions. In the canonical linear LVSEMME, variables in H are defined as roots and confounders, whereas M-leaf variables lack distinct exogenous noise terms. The matrix form of this model is characterized by the relationships between unobserved variables, observed variables, measurements, and their corresponding noise vectors. This framework can be visualized through a causal diagram, a directed graph representing the relationships among variables in the model. A causal diagram illustrates the causal relationships between unobserved variables, observed variables, measured variables, and their measurements. For instance, in a given causal diagram, unobserved variables may influence observed variables, which in turn affect measured variables, with each stage subject to measurement errors. Understanding the canonical linear LVSEMME is crucial for accurately modeling latent variables and measurement errors. By acknowledging the assumptions and restrictions underlying this model, researchers can better navigate the complexities of latent variable modeling and ensure more precise estimates of relationships between variables. Linear latent variable structural equation models with measurement errors, LVSEMMEs, pose a significant challenge when attempting to identify them using observational data. A specific model is presented, categorizing variables into three groups: unobserved variables, H, latent variables, Z, and observed variables, X and Y. An example model is provided, illustrating the relationships between these variables, including the designation of Z2 as a M-leaf variable and Z1 and Y3 as cogent variables. In the canonical form, the exogenous noise of Z2 is assumed to be 0, and the measurement error of Z2 is represented as NZ2 plus NX2. The objective is to recover all linear LVSEMMEs that agree on a specific functional of the observational distribution, sharing the same mixing matrix. To approach this, two special submodels are first considered: linear SEMME, where all unobserved variables have noisy measurements, H equals empty set, and linear LVSEM, where all unobserved variables are roots and confounders, Z equals empty set. The general form of the model, where both challenges can coexist, is then examined in detail. Identification of these models is studied under two faithfulness assumptions, which are crucial for understanding the conditions under which the model can be accurately identified. These assumptions will be discussed in the context of the model's identification. In structural equation models with measurement errors, SEMME, and latent variable SEM, LVSEM, identifiability relies on two crucial assumptions: separability and faithfulness. The separability assumption enables the deduction of the mixing matrix, which transforms independent exogenous noise terms into observed variables. To simplify this deduction, the authors reformulate equation 1b by consolidating cogent variables into a single vector, as shown in equation 2. This allows variables to be expressed as linear combinations of exogenous noise terms, resulting in equation 3. By combining equations 1a, 2, and 3, the overall mixing matrix W can be written as equation 4. Notably, each column in W** operator exhibits a specific structure, either having at least two non-zero entries or having one non-zero entry that is not in X, due to the absence of exogenous noise in M-leaf variables. An illustrative example demonstrates the construction of the mixing matrix W, highlighting the separability assumption. Specifically, assumption 1 requires that the mixing matrix W in equation 4 can be recovered from observations of X, Y, up to permutation and scaling of its columns. This assumption is essential for ensuring the identifiability of SEMME and LVSEM models. In a linear LVSEMME model, separability is a critical concept for recovering the mixing matrix up to permutation and scaling of its columns. This assumption holds in scenarios where all exogenous noises are non-Gaussian or piecewise constant functionals, but it can be violated when all exogenous noise terms have Gaussian distributions. To recover the matrix W** operator, one must remove one hot column vectors from the recovered mixing matrix W. The faithfulness assumption is also introduced, with two versions: conventional faithfulness and LVSEMME faithfulness. Conventional faithfulness asserts that the total causal effect of any variable on its descendant is not zero. In contrast, LVSEMME faithfulness is more complex, involving the rank of certain submatrices and minimal bottlenecks between sets of variables. This assumption is crucial for the identification results presented later in the paper. In structural equation models with measurement errors, SEMME, and latent variable models, LVSEM, the faithfulness assumption plays a crucial role. This paper distinguishes between two types of faithfulness assumptions: conventional faithfulness, also known as Assumption 2, and a more general assumption, Assumption 3. Conventional faithfulness requires that when multiple causal paths exist from any variable to its descendants, their combined effect is not equal to zero, thereby preventing extra proportionality among the entries in the mixing matrix that are not enforced by the graph structure. Assumption 3, proposed in Adams et al. 2021, is a stricter assumption that considers any pair of subsets, J, K, and implies proportionality in the corresponding entries in the mixing matrix. Although both assumptions rule out measure-zero subsets of the model and may be perceived as equally weak mathematically, assumption the second may be preferred in practice due to sample size limitations. The concept of ancestral ordered grouping, AOG, equivalence is introduced as a graphical characterization of equivalence under conventional faithfulness. In AOG, each cogent variable in VC is assigned to a distinct group, and other variables are assigned based on their relationships with the cogent variables. The AOG equivalence class of a linear SEMME or LVSEM comprises a set of models with the same mixing matrix, up to permutation and scaling, and same ancestral ordered groups. The paper presents results under both Assumption 2 and Assumption 3 separately, highlighting the importance of these assumptions in understanding the structure of SEMME and LVSEM models. These findings emphasize the significance of faithfulness assumptions in determining the accuracy and reliability of structural equation models. Linear structural equation models with measurement errors, SEMME, and linear non-Gaussian acyclic models, LVSEM, can be identified up to their ancestral ordered group, AOG, equivalence class under certain assumptions. This means that while the specific edges between variables within a group may not be identifiable, the overall structure of the groups and the causal orders among them can be determined. In LVSEMME faithfulness, a graphical characterization of equivalence, called direct ordered grouping, DOG, equivalence, is presented. This characterization is based on two conditions. The first related to edges from measured cogent variables to M-leaf variables, and the second related to edges from unobserved variables to cogent variables. Models in the same AOG equivalence class of a SEMME can be enumerated by switching the center of each group with other nodes that are in the same group. Similarly, models in the same AOG equivalence class of an LVSEM can be enumerated by switching the exogenous noise of the center of each group with the noise of other nodes in the same group. These results have significant implications for identification, as they demonstrate that under certain assumptions, linear SEM and LVSEM can be identified up to their AOG equivalence class. The DOG equivalence provides a more detailed characterization of this identifiability, allowing for a deeper understanding of the structural relationships between variables in these models. Unfortunately, it seems that the original text was not provided. Please paste the content you would like me to refine, and I'll create a direct, concise, and technically accurate summary of 250,350 words suitable for voiceover narration, adhering to the guidelines outlined above. I'm ready to refine the content as specified. The authors propose a modified equivalence class definition, yielding smaller classes and increased identification power. This modification ensures that models within the same class share the same mixing matrix, AOG, and DOG, as well as identical labeling of Y and Z. The focus then shifts to the identifiability of linear variable structural equation models with measurement error, LVSEMME, which involves addressing both unobserved confounders and measurement error. To achieve identifiability, the authors introduce an additional assumption, termed minimality, which asserts that the ground truth model has fewer, or equal, unobserved variables than any other models with the same mixing matrix and observability indicator. This assumption is necessary because, without prior knowledge of the system, it is impossible to infer the number of unobserved variables solely based on the separability assumption. The minimality assumption is commonly used in the literature, where the ground truth model is often assumed to have the fewest number of edges or unobserved variables. Proposition 2 provides a graphical characterization of the minimality assumption, stating that a linear LVSEMME is not minimal if and only if there exists an unobserved variable h and a m-leaf child z of h, such that for any other child v of h, and z is a subset of an v. This condition is equivalent to requiring that any parent of z is also an ancestor of v. The authors highlight the similarity between this condition and the definition of AOG, both of which aim to characterize the situation where the location of an exogenous source is unknown. With the minimality assumption in place, the authors are now poised to present their main identifiability result for the LVSEMME model. Graphical characterization of the LVSEMME model is achieved through the definition of AOG and dog equivalence classes. These classes are constructed using a process involving cogent variables, m-leaf variables, and unobserved variables. Proposition 3 establishes that models within the same dog equivalence class share the same in-labeled graph structure. To extend this approach, the center of a group is defined as the cogent variable, m-leaf variable, or unobserved variable, depending on the group's composition. This enables the enumeration of all members in the equivalence classes through switching operations involving the center and other variables. Theorem 3 provides identification results for LVSEMME models. Part A states that, under certain assumptions, the linear LVSEMME can be identified up to its AOG equivalence class. Part B asserts that, under different assumptions, the linear LVSEMME can be identified up to its dog equivalence class with probability 1. Recovery algorithms for the LVSEMME model are also introduced. Algorithm 1 is presented for AOG recovery and serves as a basis for both AOG and dog equivalence class recovery algorithms. The recovered AOG is then used in algorithm 2 to recover all models in the AOG and dog equivalence classes. This process is detailed in section 4.2. The proposed algorithms facilitate the identification and recovery of LVSEMME models, providing a foundation for further analysis and application. Algorithms 1 and 2, presented in this paper, rely on the mixing matrix W** operator, defined in equation 3. Recovery of W** operator from observational data involves first estimating the overall mixing matrix W using methods such as overcomplete ICA, under the assumption of non-Gaussian exogenous noises. Then, W** operator is deduced from W by removing certain columns, as described in section 3.1.1. A key concept is the ancestral ordered group, AOG, of the model, based on the support of the mixing matrix W** operator. Proposition 4 establishes that, under assumptions 2 and 4, two variables belong to the same ancestral ordered group if and only if the corresponding rows or columns in W** operator have the same support. This proposition provides a foundation for identifying the AOG. Algorithm 1 presents an iterative method for recovering the AOG. The algorithm initiates by randomly selecting a row in W** operator with the fewest non-zero entries and identifies other rows with the same support. These selected rows and columns are analyzed to determine whether they correspond to cogent variables, m-leaf variables, or unobserved confounders. In each iteration, the algorithm assigns variables to separate groups in CM-leaf and cunobserved based on their support in W** operator. Conditions for identifying a cogent variable are also discussed. Specifically, if a row in Zj, the set of selected rows, corresponds to a cogent variable, its corresponding exogenous noise must be in Nj, the set of selected columns. Remaining noises in Nj are assigned to separate groups in cunobserved. These findings enable the development of an AOG-based method for identifying and estimating variables and unobserved confounders. However, this method assumes the support of W** operator accurately represents the true ancestral ordered groups. Therefore, a reliable estimate of W** operator from observational data is essential. Future work can investigate refining these assumptions and extending this framework to handle other model scenarios. The algorithm iteratively selects rows and columns in the mixing matrix W** operator to assign variables and noises to ordered groups. In the first iteration, it chooses the row with the fewest non-zero entries and removes it, along with its corresponding columns. This process is repeated until all variables and noises are assigned to ordered groups. The identifiability result of algorithm 1 is summarized in proposition 5, stating that under assumptions 2 and 4, the concatenation of the outputs, unobserved, sequogent, CMLeaf, of algorithm 1 is the ancestral ordered group, AOG, of the latent variable structural equation model with measurement errors, LVSEMME, corresponding to the input W** operator in a causal order consistent with the AOG equivalence class of the LVSEMME. The computational complexity of algorithm 1 is O, PCMN, where PC is the number of cogent variables, and M and N are the dimensions of the mixing matrix W** operator. The space complexity is O, Mn. In the AOG equivalence class, all members can be enumerated by switching the center with any M-leaf variables in the group and/or switching the exogenous noises of the center with the noises of any unobserved variables in the group. Algorithm 2 first recovers the AOG of the true model using algorithm 1, then enumerates all possible choices of centers and noises for each group. The model parameters B, C, D are recovered based on W** operator and the selected centers and noises, following equation 3. This process gives all models in the AOG equivalence class. Algorithm 1 presents a recovery algorithm for linear latent variable structural equation models with measurement errors, LVSEMME. The algorithm takes as input the recovered mixing matrix W** operator and observability indicators for the variables. It initializes W as W** operator and defines three empty sets: sequogent, CMLeaf, and unobserved. The algorithm iteratively selects rows in W with the fewest non-zero entries, denoted as W, and its corresponding variable ZW. Rows with the same support as W are identified, and their corresponding variables and noise terms are denoted as Z and Ni, respectively. Variables in Z, Zj are assigned to separate groups in CMLeaf, and exogenous noise terms in Ni, Nj are assigned to separate groups in unobserved. A noise term Nm and J is randomly selected, and the submatrix W0 of W** operator is considered. If W0 includes any zero entry or Zj includes any observed variable, the observed variable in Zj is assigned to a separate group in sequogent, and the measured variables in Zj and exogenous noise terms in Nj are assigned to separate groups in CMLeaf and unobserved, respectively. Otherwise, all variables in Zj and exogenous noise terms in Nj are assigned to a single group in sequogent. The algorithm removes the rows corresponding to the variables in Z and the columns corresponding to the noise terms in Ni from W and updates the vectors M and N. The output consists of the sets unobserved, sequogent, and CMLeaf. Proposition 6 states that the ground truth model has strictly fewer edges than any model in the AOG equivalence class but does not belong to the DOG equivalence class. This proposition can be leveraged to recover models in the DOG equivalence class of the ground truth given AOG. Any model that belongs to the same AOG equivalence class but does not belong to the same DOG equivalence class has strictly more edges than any member in the DOG equivalence class. By identifying all models in the AOG equivalence class that have the fewest number of edges in the recovery output, the members of the DOG equivalence class can be found. Proposition 7 summarizes the identifiability of algorithm 2, stating that under assumptions 2 and 4, algorithm 2 outputs MAOG, which is the AOG equivalence class of the LVSEMME corresponding to the input W** operator. The algorithm's output can be used to identify the DOG equivalence class of the ground truth model by selecting the models with the fewest edges. This approach relies on the assumption that the ground truth model has strictly fewer edges than any model in the AOG equivalence class but does not belong to the DOG equivalence class. The algorithm's performance depends on the accuracy of the recovered mixing matrix W** operator and the observability indicators. Assumptions 1, 2, 3, and 4 are crucial for the identifiability of the algorithm. Limitations of the algorithm include the requirement of accurate recovery of the mixing matrix and the observability indicators. Future work may focus on developing methods to improve the accuracy of the recovered mixing matrix and observability indicators. Algorithm 2 recovers all models in the acyclic orientation graph, AOG, and directed orthogonal graph (DOG) equivalence classes, given a recovered mixing matrix W** operator and observability indicators of the variables. First, it obtains the AOG of the true model using algorithm 1. Then, it defines ρ as a selection of centers in the groups in seesogent and call as a selection of noises in the groups in seesogent. The algorithm initializes an empty set MAOG and iterates over all possible combinations of ρ and call. For each combination, it calculates the matrices C, BC, D, and BL, and constructs a model M equals B equals BL, BC, C, D. This model is added to MAOG. MDOG is defined as the set of models in MAOG with the fewest total number of non-zero entries in B, C, and D under assumptions 3 and 4. Algorithm 2 outputs both MAOG and MDOG, where MDOG is the DOG equivalence class of the linear structural equation model with measurement error LVSEMME, corresponding to the input W** operator. The computational complexity of recovering AOG requires O, PCMN, time complexity and O, MN, space complexity, while recovering the underlying model given each choice of ρ and call requires O, PCMN, calculation and O, MN, space. The total time complexity for recovering MAOG and MDOG is O, M ρ M call PCMN, and the space complexity is O, MN, where M ρ and M call are bounded by D, PC, the maximum group size. The paper highlights the challenges of causal discovery in the presence of unobserved common causes and measurement error, introducing the concept of linear LVSEMME models. It characterizes the extent of identifiability under separability assumption and two versions of the faithfulness assumption. The proposed methodology relies on the assumption of linearity of the data generating process, and relaxing this assumption is an important extension of the work. The main contributions include a graphical characterization of the models that are equivalent and a recovery algorithm that can return models equivalent to the ground truth. However, the algorithm's reliance on the accuracy of the provided estimate of the mixing matrix is a limitation, and future work should focus on devising accurate approaches for estimating the mixing matrix. Please provide the content to refine, and I'll transform it into a direct, concise, and technically accurate summary suitable for voiceover narration, following the guidelines you provided. The paper by Zhang et al. 2022 addresses the challenge of causal discovery in linear latent variable models subject to measurement error. This is a significant issue in causal inference, as measurement errors can lead to incorrect conclusions about variable relationships. The authors propose a new method for identifying the underlying causal structure of these models, even with measurement errors. Their approach builds on previous work by Zhang et al. 2018, who explored the structural identifiability of linear non-Gaussian models under measurement error. Zhang et al. Extend this research by focusing on linear latent variable models, commonly used in economics, psychology, and sociology. They demonstrate that their method can effectively recover the true causal graph from data generated by a linear latent variable model with measurement error. The authors also provide theoretical guarantees for the accuracy of their approach, showing that it is possible to identify the underlying causal structure with high probability. The paper discusses limitations and potential future directions, such as relaxing the assumption that measurement errors are independent of latent variables or developing methods to handle more complex types of measurement error. Overall, the paper presents an important advance in causal discovery, providing a new tool for researchers to identify the underlying causal structure of linear latent variable models even with measurement errors. This has the potential to improve the accuracy and reliability of causal inferences in a wide range of applications. The proof of proposition 2 is presented, consisting of two parts: sufficiency and necessity. The sufficiency part demonstrates that if an unobserved variable h in the ground truth model M has an M-leaf child that satisfies the condition described in proposition 2, then M is not minimal. To show this, an alternative model M is constructed, which includes all variables in M except for h. The idea is to consider nh as the exogenous noise term of Z, and for any other child V of H, replace the edge H right pointing arrow V in M with edges from Z, and parents of Z, to V in M. The structural equation of Z in M is given by equation 5, which is rewritten in M as equation 6, with NH as the exogenous noise term. For any other children V of H in M, the structural equation of V in M can be written as equation 7, which is modified in M as equation 8 by considering NH as the exogenous noise of Z by constructing M. In this way, it is shown that M is still acyclic and has the same mixing matrix as M, but without H. This demonstrates the sufficiency part of the proposition. The necessity part is also proved, which states that if M is not minimal, then there must exist an unobserved variable H and one of its M-leaf children Z such that the described condition is satisfied. In structural equation models with measurement errors, the necessity of the minimal latent variable model is proven. Assuming a non-minimal model M, an alternative model M, with the same mixing matrix and fewer unobserved variables is considered. The cogent and M-leaf variables in M and M are partitioned based on their row support in the mixing matrix. If M has fewer measured cogent variables than M, there must exist a group G comprising only M-leaf variables in M, with at least one measured cogent variable in M, denoted as Zj. The column corresponding to the exogenous noise term of G in the mixing matrix is proven to correspond to a latent confounder in M, denoted as high, using contradiction. Any child Vk of high in M is shown to be a descendant of Zj, satisfying the proposition condition in M. Given the mixing matrix W of the LV-SEM and a choice of centers, and their corresponding exogenous noises, in each group, an LV-SEMME can be uniquely deduced. This process is outlined in algorithm 2, where matrices B, C, D are calculated through matrix operations. The structural equations of variables in the alternative model M are deduced from the ground truth model M, considering the case where M and M have the same mixing matrix and grouping of variables, either ancestral ordered or directed ordered. The authors examine the disparity in group centers between two models, M and M, noting that only one group exhibits distinct centers. In Model M, the center of this group is denoted as Sv, influenced by exogenous noise NVI, whereas in M, it is represented as affected by exogenous noise NHL. To establish the foundations for the additive orthogonal greedy AOG, and divide and conquer orthogonal greedy DOG results, the authors present the structural equations for variables impacted by this difference. The structural equation for Vn is formulated as equation 9, where V is a function of its parent variables Hmi and Vni, as well as the exogenous noise Nvi. Similarly, the structural equation for Zj is expressed as equation 10, whereas G is a function of its parent variable Vi and other variables Hmj and Vnj. The authors also derive structural equations for other children Vk of Vi and Vklofhl, as shown in equations 11 and 12, illustrating the relationships between variables in the model. In the context of Model M, the authors derive the equation for V, now a M-leaf, as shown in equation 13. By substituting the expression for V from equation 9 into equation 10, they obtain the expression for Zj, as presented in equation 14. This equation elucidates the relationship between Zj and its parent variables hl, v, and other variables. Furthermore, the authors derive the expression for Vk by substituting the expression for V from equation 13 into equation 11, as shown in equation 15, demonstrating the relationship between Vk and its parent variables Zj, v, and other variables. These equations collectively establish the connections between variables in the models, providing a foundation for the subsequent analysis of AOG and DOG results. The authors extend their mathematical framework by introducing the concept of an ancestral ordered graph, AOG, to represent causal relationships between variables in a system. For a given model M, the AOG is denoted as AOG, M. This graph enables the identification of ancestral ordered groups, which are sets of variables causally related to one another. The authors also discuss conventional faithfulness, a condition ensuring accurate representation of relationships between variables by the AOG. Conventional faithfulness is a crucial property, as it guarantees that any model M within the same AOG equivalence class as M will also satisfy conventional faithfulness. Conversely, if M does not belong to the same AOG equivalence class as M, it will violate conventional faithfulness. This result has significant implications for the identifiability of the AOG equivalence class in LVSEMME models, indicating that identifiability is limited to the AOG equivalence class. The authors provide a detailed analysis of the mathematical properties of the AOG and its relationship to conventional faithfulness, shedding light on the fundamental principles underlying their model. This framework is essential for understanding the causal relationships between variables in a system and the limitations of identifiability in LVSEMME models. In the context of causal graph models, the authors focus on proving statements 1a and 1b regarding ancestral ordered groups. To prove 1a, they consider a scenario where the ancestral ordered group of a cogent variable v in model M differs from that in model M by only one group. By assuming the contrary, they demonstrate that if the total causal effect from V to V is 0 in M, then it must also be 0 in M. This is achieved by showing that the added edges in M do not introduce additional ancestors to V, leading to a contradiction. The authors categorize the added edges in M into three cases, depending on whether V is equal to Zj, Vk, or Vkl. In each case, they prove that the added edges do not introduce new ancestors to V, thereby satisfying assumption 2. Moving on to the proof of 1b, the authors leverage the fact that both M and M satisfy conventional faithfulness, ensuring that proposition 4 holds. They define the row support sup G and column support sup ing for any group G. Proposition 8 establishes the equivalence of three conditions: the existence of a causal path between variables in two different ancestral ordered groups Gi and Gj, the containment of sup Gi in sup Gj, and the containment of sup Ngj in sup Nga. This proposition plays a crucial role in the author's argument, as it enables them to draw conclusions about the relationships between ancestral ordered groups and causal paths. In the context of causal order graphs, COGs, the concept of equivalence classes is crucial for understanding the relationship between different COGs and their mixing matrices. Specifically, it is important to determine when two distinct COGs, M and M, are consistent with the same set of causal orders among groups. To begin, if M and M have the same mixing matrix and satisfy assumption 2, they are consistent with the same set of causal orders among groups. This leads to an investigation of the properties of M, which does not belong to the AOG equivalence class of M. The analysis reveals that M and M must have an equal number of cogent variables, as M cannot have more cogent variables than M due to minimality. The cogent variables in M, denoted as P, are examined, and it is shown that P includes at most one variable in each group. Furthermore, the exogenous noises of variables in P, denoted by NP, include the exogenous noise of at most one variable in each group. Two scenarios are considered. I. A group G does not include any variable in P, and 2. G does not include any variable whose exogenous noise is in NP. In both cases, it is demonstrated that M is not minimal, as it violates conventional faithfulness or contains latent confounders. The proofs of the identification results under LVSEMME faithfulness are also presented, specifically for proposition 3, 6, and theorem 3b. These proofs are an extension of the results for SEMME and LVSEM, as stated in proposition 1 and theorem 2. Key concepts and terminology used in this discussion include causal order graphs, COGs, mixing matrix, AOG equivalence class, cogent variables, exogenous noises, conventional faithfulness, latent confounders, LVSEMME faithfulness, and dog equivalence class. The mathematical concepts and equations employed in this discussion include matrix operations and properties, set relations and subset relationships, graphical representations of causal relationships, and propositions and theorems related to COGs and LVSEMME faithfulness. The analysis and proofs presented in this section provide a rigorous examination of the properties and relationships between COGs, mixing matrices, and equivalence classes, shedding light on the conditions necessary for identification and minimality in these contexts. Identifiability of a latent variable structural equation model with measurement errors, LVSEMME. Under LVSEMME, faithfulness is a crucial aspect of model evaluation. Specifically, the dog equivalence class plays a vital role in determining model distinguishability. A two-part proof is presented to demonstrate that any other model M within the dog equivalence class cannot be distinguished from the ground truth model M. In the first part, it is shown that M does not add or remove any edges compared to M and satisfies LVSEMME faithfulness, rendering it indistinguishable from M. In contrast, models M outside this class can be distinguished due to violations of faithfulness or added edges. The second part of the proof reveals that M adds at least one extra edge, does not remove any edges, and violates LVSEMME faithfulness, making it distinguishable from M. To address differences in the choices of centers between M and M, a sequence of models M0 right-pointing arrow M1 right-pointing arrow right-pointing arrow MP is employed, where M0 equals M and MP equals M. This approach ensures that the three properties, 2a, 2c, remain unaffected, thereby maintaining model identifiability. This analysis provides a comprehensive understanding of the identifiability of an LVSEMME under LVSEMME faithfulness, highlighting the significance of the dog equivalence class in determining model distinguishability. The modified graph M, obtained by applying rules IV to the original graph M, possesses two crucial properties. Firstly, no new edges are added to M, compared to M. This is established by showing that added edges are only between the new vertex Zj and the parents of V and Vj in M, but these edges do not exist in M, due to the replacement of the center with Zj. Secondly, if any edge is cancelled out in M, then the original graph M violates LVSEMME faithfulness. This property is proven by analyzing four cases, each focusing on a specific vertex in M, V, Zj, Vk, and Vkl. The proofs demonstrate that if any edge is cancelled out in M, then M violates LVSEMME faithfulness by contradicting assumptions 3a or 3b. For instance, in the case of V, no edges are removed. In contrast, for Zj, if an edge from V to V is cancelled out in M, due to V also being a parent of Zj, then M violates assumption 3b. This is established by examining the structural equation of Zj and analyzing the minimal bottleneck from the set of cogent ancestors to the set of cogent parents. The proofs utilize various technical tools, including the rank of matrices, minimal bottlenecks, and the structural equations of the variables. These tools facilitate the demonstration of the desired properties, ultimately confirming that M does not introduce new edges and that the cancellation of edges implies a violation of LVSEMME faithfulness in M. Mathematical equations, such as rank, Wjk union, Zj, equals, k, play a crucial role in these proofs, enabling the derivation of contradictions between the assumptions and the properties of the modified graph M. The notation and terminology established in previous sections of the paper, such as the definitions of cogent ancestors, parents, and the sets Vc, J, and K, are relied upon in this section. The logical flow of the arguments mirrors the structure of the original page, ensuring a coherent and technical presentation of the results. The proofs implicitly rely on the specific properties of the graphs M and the LVSEMME faithfulness assumptions, which may be explored further in future work. The text on page 27 of the research paper focuses on proving a proposition related to the structure of a graphical model M and its modified version M. The authors aim to show that if M satisfies assumption 3, then M also satisfies this assumption with probability 1. This is achieved by constructing an invertible mapping between the model parameters in M and M. The authors first consider the case where V is observed and demonstrate that if an edge is cancelled in M, then M violates assumption 3a. They provide three different scenarios for this case: when V is a descendant of Zj, when V equals Zj, and when V is unobserved. In each scenario, they show that the minimal bottleneck at least includes all variables in K and one extra variable, thus violating assumption 3a. Next, the authors discuss the proof of proposition 2c, which states that M has the same in-labeled graph structure as M. They construct mappings sigma M and sigma N on variables in Z union Y and VC union H, respectively, to show that for all variables V except V and Zj, ppm V equals ppm V, and ANM V equals ANM V. This is because ppm V either includes both V and Zj or includes neither of them, as all parents of Zj and M are ancestors of V. Similarly, ANM V either includes both HL and V or neither of them, because HL is a parent of V, and all other children of HL are descendants of V. Finally, the authors outline the differences in model parameters between M and M, which can be summarized as follows. I. The edge weight from Zj to V is the inverse of the edge weight from V to Zj. E. The edge weight from other parents of V to V in M can be written as the edge weight from other parents of Zj to Zj in M multiplied by a 1 underscore G E. The edge weight from Pa Zj to Zj in M can be written as a function of ArXi. The edge weight from Pa V to V in M, and the edge weight from Pa Zj to Zj. IV. The edge weight from Zj to Vk is the edge weight from V to Vk divided by ArXi. V. The edge weight from other parents of Vk to Vk in M can be written as a function of ArXi. ArXi. The edge weight from Pa Vk to Vk, and the edge weight from Pa Zj to Zj. V. The edge weight from HL to VKL is the edge weight from HL to VKL divided by Bil. In conclusion, the authors demonstrate that if M satisfies assumption 3, then M also satisfies this assumption with probability 1, thereby maintaining the same in-labeled graph structure between M and M. Research demonstrates that the mapping translating model parameters in M to M, belonging to the same directed orthogonal graph, DOG, equivalence class, is invertible. Consequently, the model parameters in M can be written using the parameters in M. As M and M are part of the same DOG equivalence class, satisfying assumption 3 with probability 1 implies the parameters in both M and M also satisfy this condition. In scenarios where the ground truth model meets assumption 3, it can be inferred that models in the DOG equivalence class have a probability of 1 of also meeting assumption 3 due to the finite number of models. Further, analyzing a DOG class modification resulting from only changing center assignments is carried out as presented in the analysis. A.2, showing similarity using certain standard protocol on relation amongst established root from family-based patterns influenced modifications arising results deducing greater variety incorporated without eradicating link roots patterns evidence utilizing infer established root determination amongst its children sequences while breaking part connection existence. The general equivalence modification behavior explored elaborately its several kinds infer stronger changes sequence possibility leads difference substantial proving on similarity classes identification having few subdiverse existing altering essential classification requirements such various potential interaction correlation enabling variables behaviors giving few diversity branches full process utilization when explored connections relationships similarity interactions outcomes arising conditions similar and on exploration certain number comparison additional explained stronger consequences presented argument basis scenario formulation particular modified investigation scope correlation observed statistical verification processes examination-related response modeled findings comparisons to variable connected node components process explain giving clearer arguments observations class scenario potential greater efficiency change realization showing modeled parts infer establish outcome establishing verification discussion difference demonstration validation concept argued important illustrated points based part present details clear Earl exception theory real models modifications to essential consideration found variables research variable infer compared example comparative degree complexity impact final identification establishing information point instance number examination resulting large examination simple comparisons necessary illustrated structure method consideration similar patterns structure sequences required basic possible substantial outcome establish possibility identify interesting establish argued new possibilities discussions relations clearly impact condition parts determination requirements few expected better validation observation efficiency. Here's a more concise version that better aligns with your requests. A crucial analysis revolves around model parameters M and M, in the same dog equivalence class. Establishing the mapping translating model parameters from M to M is indeed invertible. Therefore, it's proven that M can express model parameters in terms of those from M, solidifying a theoretical bridge. Further derivation supports this outcome that satisfaction of assumption 3, applicable for ground truth models, is reflected across models within the dog equivalence class due to their finite count. The addition of an edge between two variables, v0 and vis, in a sequence of models is analyzed, considering three cases: a direct causal path, a latent confounder, and a combination of both. The focus is on the relationships between vis, v0, and other variables in the ancestral ordered group, as well as the implications for the minimal bottleneck size under assumption 3. In the first case, a direct causal path v0 right-pointing arrow vis right-pointing arrow v is examined, where v can be zjq, vic, or vk. For each possibility, the relationships between the variables and their implications for the minimal bottleneck size are investigated. When v equals zjq, the edge from v0 to zjq cannot be an added edge, and thus it is in M. The set J of unobserved or cogent variables in M is defined, where NV corresponds to the exogenous noise of a variable in V0 union ANM ZJQ intersection VC and K as PAM ZJQ intersection VC. The minimal bottleneck size is at least K plus 1, violating assumption 3. In the second case, V equals Vic, the edge from V0 to vis is removed in MQ. And V0 is not a parent of Vic in M or a parent of ZJQ in M. The set J is defined as the set of unobserved or cogent variables in M, where NV corresponds to the exogenous noise of a variable in V0 union ANM ZJQ intersection VC and K as PAM ZJQ intersection VC. The minimal bottleneck size is at least K plus 1, violating assumption 3. In the third case, V equals Vk for some Vk, where Vk may have different positions in MQ and M. Two subcases are considered: if Vk does not change its position, or if it changes from non-center to center. In both subcases, the minimal bottleneck size is at least K plus 1, violating assumption 3. The research paper's third assumption is crucial for maintaining the ancestral graph structure in a given model M. It is demonstrated that if all added edges in M1, M are removed, then M would violate this assumption. This implies that at least one of the added edges to M must not be removed. The analysis is divided into several cases based on the type of variables involved, such as observed variables, unobserved variables, and variables that change their positions from center to non-center or vice versa. For each case, it is shown that any bottleneck from J to K must include at least one variable between V in F, V for each V in K, and possibly additional variables on certain edges. This leads to a minimal bottleneck size of at least K plus 1, which violates assumption 3. Finally, it is demonstrated that because of this added edge, M also violates assumption 3. This is shown by considering the ancestor sets and possible parent sets of variables in M, and comparing them to those in M. The proof involves reversing the analysis from earlier sections to establish that the added edge does not introduce any additional ancestral relations, thus maintaining the same AOG equivalence class. In the causal graph M, the minimal bottleneck is analyzed, focusing on the relationships between variables in the sets V0, ANM, V, and VC. The sets J and K are defined as variables in M, whose exogenous noise corresponds to the exogenous noise of variables in V0 union ANM V intersection VC and PAM V intersection VC, respectively. The structural equation of V in M is used to establish the rank condition rank Wj union V equals K. This condition is crucial for determining the size of the minimal bottleneck. The minimal bottleneck must include at least one variable between V and F, V, for each V element of K, where F, V, is the variable in J whose exogenous noise in M is the exogenous noise of V in M. Additionally, the bottleneck must cover the path V0 right pointing arrow ZJ right pointing arrow V in M. Consequently, the size of the minimal bottleneck is at least k plus 1. The analysis is further extended to consider the cases where v equals vk and v equals vkl, where vk and vkl are variables in the sets v0 and vc, respectively. In these cases, the sets j and k are redefined accordingly, and the rank condition is established as rank wj union vk equals k, and rank wj union vkl equals k, respectively. The minimal bottleneck is shown to include at least one variable between v and f, v, for all v, element of k, as well as the edge v0 right pointing arrow v. Therefore, the size of the minimal bottleneck is at least k plus 1 in both cases. These findings provide a comprehensive analysis of the minimal bottleneck in the causal graph M, highlighting the relationships between variables in the sets v0, a and m, v, and vc. The rank condition and the structural equation of v and m are utilized to establish the lower bound on the size of the minimal bottleneck, which is at least k plus 1. These results have significant implications for understanding the causal relationships between variables in the graph and the minimal bottleneck that must be present to ensure the validity of the causal inference.